Hello everyone. We are again back with another tech talk on a really interesting topic, JVector, Panama-accelerated embedded vector search. And we have with us Jonathan Ellis, who is a co-founder and CTO of Data Stacks. And along with the rich experience in the industry, he has been quite involved with the community driven initiatives as well. He has been a project chair of Apache Cassandra, where he not only built the Cassandra project but took the community to a open source success. He has also been admired for building a object storage system which can scale up to petabytes of data and gigabytes per second throughput. Um, okay, so first of all, welcome, Jonathan. Thank you so much for joining us at such a short period. We would also like to thank Mary from the Jug who helped us with it. And along with it, we would like to thank other Jug communities like Hyderabad, Bangalore, Kerala, and other ones who came together for making this session a success. Over to you, Jonathan.
Great, thank you. All right, I'd like to take the first 5 minutes and talk about why vector search is important. The reason is that even just 1 year ago, the way people built AI for their applications was to an application like this, build an API that could serve recommendations and predictions based on their business's data. And I've labeled 4 steps here, and you can break these down into multiple sub-steps. But I think at the high level, you need to have, at a minimum, you need to have feature extraction, you need to train a model, you need to deploy and serve that model. And then I've got label 4 is labeled feature extraction. Again, this is real-time feature extraction. Because when you're training the model, you're doing that on a static or a relatively static data set. You're doing the training in batches. But when you're making predictions in real time, as people are using your service, then you need to have those same features available to feed into the model for inference. And so that's actually a separate problem, and it's just as hard, if not harder, even though you've already done it once, to build your analytical or your data lake data set of features to train the model. So each of these steps, I would say step number 3 of deploying and serving the model, that's starting to become reasonably standardized. But each of these steps takes serious expertise. In fact, the standard is that it's going to take a team of 3 or half a dozen PhDs or people with deep AI experience to build something like this. It's even with all that experience, it's still going to take time. You're still going to make mistakes. You're still going to have to iterate on your model design and improve it. The first stab at your model probably isn't going to work. You'll have to learn from what happened and build improvements. And all of this costs money. It costs money to clean your data set. It costs money to run the model training. Like, all of it's expensive and time consuming. Now, the reason that generative AI is so impactful and why everyone's so excited about it is that it turns that process into something much simpler, which is basically ask the large language model a question or ask it to complete a fragment of text. You can do this with a single engineer in a few days instead of a large team in a few weeks. So it's much faster, much less expensive. The barrier to getting something useful out of this is so much lower that companies that would never have tackled the not old-fashioned, but the standard way of building AI, people who would have never done that can do this with large language models. Now, the reason that there is there's some fine print here, which is that you need to give the language model enough information to give you a useful. So as an example, I asked ChatGPT Pro, so this is, so we don't need to go into the details of that, except to say that it's a way that Cassandra merges its log structured data files to remove deleted data and merge out the most recent version of every row. And so when I asked GPT about this, it gave me the answer, which is correct. As near as I can tell, it didn't make anything up completely. So Cassandra and unified compaction have been around for a few years. They were part of the training that OpenAI did. But everything that it's giving me here is very generic. Like if I just from the name, it's a unified compaction strategy. Like that's what it's telling me. It's like regurgitating that bullet point one says it's unified. Bullet point two says it's unified. Bullet point three, it says there you can adjust compaction parameters, but that's again, it's really generic. It's not telling me anything it's not telling me anything I didn't already know. This is what it gave me when I asked the same question, but I first gave it a page of documentation about unified compaction strategy. Now it's giving me much more detailed information. It's talking about the density-based levels with a fan-out factor F and a tiering factor T. It's telling me how it works with sharding and how it does size-based levels. So it's a much better answer. So the twist on this very simple diagram I gave you is that in practice, if you want good answers, you can't just ask your question. You need to give it context sources. You need to give it information to pull from to supplement its training data to give you more specific and more useful answers. So to find the right context, this is where vector search comes in. I'm not going to go into details about where embedding vectors come from. The short version is there are specially trained machine learning models that can take sentences or multiple sentences and turn them into a vector of 384 or 1068 or 1536 dimensions, and that becomes a representation of that text that was encoded into what we call an embedding vector. So embedding just means I had text and I turned it into a vector that represents that text using one of these embedding models. So given that I have a vector representing that text, we can use some very simple math to answer which of these are actually similar. And it's not just a word-based encoding. I think it was the first. It's called word to vec. So it's word and then the number 2 VC, word to vec. That came out of Google 10 years ago in 2013. That was encoding single words into vectors. And we've made a lot of progress since then to where we can capture semantics across entire sentences or multiple sentences. So I've got some examples here where in the first example, these two sentences, man bites dog and dog bites man, those contain the same terms, So an embedding vector will capture the difference between those two sentences, even though they have the same words in them. In the next two examples, I have sentences that do not contain words in common, but they have similar semantic meanings. So an embedding vector will also capture the similarity in those meanings despite not having words in common. And the way we do that is we compute a cosine similarity or a dot product similarity of those vectors, and that gives us a single number, a float 32 typically, that tells us how similar these vectors are, and by extension, how similar the text was. And then the last piece is that when you train the models that generate these embeddings, you're not just training it on similarity on a blank slate, questions and answers as well. So that's why when I said, summarize, given a data set that I turn, how can I pull out the most relevant, the most similar vectors that are associated with a query so that I can retrieve the correct context and give it to my language model to give me a better answer. And the term that you'll see in the research is KNN, stands for K nearest neighbors. And the reason that this is such an interesting research problem is that nobody knows how to solve this efficiently and exactly for high dimensional vectors. If I have a vector of 2 or 3 dimensions, then I can use things like a quad tree or a KD tree to do a divide and conquer search algorithm, and that's going to give me the correct answer in sublinear time. But at high dimensions, those approaches don't work. When I said at the beginning, 384 dimensions is a relatively small text encoding vector, and that's completely inappropriate for a KD tree. So what the state of the art is to do approximate nearest neighbor search. And I've represented the two broad categories of approaches that people solve this with in this slide. So on the left, I've represented partitioning. One approach is to partition my vectors that I need to search, and at search time, I will pick the partitions that are closest to my query vector, and then I'll only look in those close partitions for the nearest neighbors. So in this example, I have a 2-dimensional Voronoi field, and what that means is the blue lines are enclosing areas that are closest to the red asterisk in the center. And this is actually something that you can do at higher dimensions than 2. And inverted Voronoi field is a very popular way to tackle this kind of partitioning index. On the right is a graph, and that's the other main category of nearest neighbor index that people build, is graph-based indexes, where the challenge is to select appropriate edges to add between vectors in your data set so that you can perform a search and have a high chance of finding the closest vectors to your query. It's not guaranteed to be the closest vectors. You only get it guaranteed if you have a fully connected graph, which would take exponentially long time to search. So we're not going to do that. Instead, we're going to pick a relatively small degree of 32 or 64 edges per vector, and then we'll fill those edges with what we think are the best connections to make that search go well. And picking those best connections, that's where things get interesting. I'll talk a little bit more about the approach that JVector uses in just a bit. First,
Before going to ANN, can you give some details about the embedding model? Because that is the one which is going to determine the quality of your search, right? The embedding model which you just were describing earlier.
yes.
Even before we process the query, we need to convert the text query into a vector embedding, right? And that is done through embedding model. So can you talk something on that?
Do you want to talk about how the model is created, or just which model to use to solve problems?
Right. So some details basically, do we have standard embedding models, or they are also curated ones?
So I'll tell you what people are doing, and then I'll tell you what they should be doing. What I'm seeing in people using our vector search database, our vector search as a service, which is called DataStax Astra. What I'm seeing there is that almost everyone is using OpenAI's embedding service. And this is the reason why I understand why they do it. They do it because it's easy, it's not expensive, and it's reasonably fast to compute the embeddings. However, the reason why it is not optimal and people should be using other models is that the embedding vectors generated are not optimized. They're very large, and everything in vector search is proportional to how large your vector is. If your vector is twice as large, it will take twice as long to do searches for those vectors, because doing a search involves computing similarity between your dataset embeddings and your query embedding. So if your embeddings are twice as long, computing those similarity, no matter what similarity metric you're using, it's going to be linear in the size of the vector. So I mentioned that 384 is on the small end of vector embedding models. That's the size generated by E5 V2 small. So I'll put that in the chat here. So the family is E5 V2, and then the specific they have three sizes. There's a standard size, there's a small size, and a large size. And the standard and large outperform OpenAI in relevance tests, and the small ones come very, very close. They're like 99% as good as OpenAI's, but they're 1/4 the size. So OpenAI's are 1536 dimensions, where each dimension is a float 32, so it's about 6 kilobytes. And the E5 small v2 are 384, so it's 1/4 the size. So that's my recommendation for a general purpose embedding model to use. And that's open source, it's freely available, it's on Hugging Face, super easy to deploy. And I believe it's available on Hugging Face's embeddings as a service as well. So if you don't want to bother dealing with infrastructure to have a microservice that serves embeddings, that's really easy to build. But if you don't want to do it, there are people hosting it for you. So that would be my recommendation.
Okay, thanks.
Mm-hmm. So if there's a website called ANN Benchmark, and they have dozens of projects, most of them are open source, not all of them, that perform approximate nearest neighbor search. And for this slide, I've picked the data set that has the smallest number of lines on the graph, just because it's impossible to read a graph with 50 lines on it. This has about a dozen, which is more tractable. And I can break down those dozen lines further by those categories that I just talked about. There's the partitioning category, and there's the graph category. There's actually a third category, which is obsolete stuff that you shouldn't care about. So first, that's these first five. So you've got annoy, you've got some other stuff we don't care about. These are the partitioning based ones that are more or less state of the art. So there's one from Face, which is a C++ library from Facebook Research with Python bindings. And so there's actually multiple ways you can configure Face. And you can see at the top, it's the third entry from the top right. This one is Face IVF PQFS. And what that means is it's inverted Voronoi field, so it's the partitioning approach. It's doing product quantization, that's the PQ, and it's using a fast scan search algorithm. And all of those are kind of toolbox components that you can combine in Face to get different index behaviors. Then the blue line or the teal line is a scan from Google Research, which is also a fast scan approach. But with scan, you don't get to mix and match the configurations. It's just basically one design, and that's what you get. It's one of the higher performing algorithms in the ANN benchmarks. And then this next slide, this shows the graph-based algorithms. So most of these, you can see there's HNSW from Face, the same Facebook library, HNSW from Vespa, HNSW-lib, which is the original implementation of HNSW. There's, let's see, Glass in the top right. Glass also implements HNSW. So Weaviate, lower right, also implements HNSW. So there's a pattern here, which is, like I said, graph is the general category, but we're looking at these, it's like HNSW, HNSW. There's a lot of HNSW. And the reason is that HNSW gives you high performance, and it also gets you high recall, so high accuracy. So recall measures, if what you do is you take your data set, your test data set, and you do a brute force calculation of what the exact nearest vectors are. And then you compare your approximate algorithm with the results that you got with your much slower exact search. And so most of the data sets, they will pre-compute the top 100 closest vectors. And so then the question is, how many of those 100 closest vectors did your ANN search come back with? So if I came back with 97 of the top 100, my recall is 97%. So with the partitioning approaches, those tend to be lower recall. Generally speaking, if you're getting 50% recall with a partitioning algorithm, you're doing pretty well. And that's completely fine for some applications. But when you need higher recall, then it's difficult to get that with a purely partitioning-based approach. And graph-based algorithms like HNSW do a lot better. The other reason that everyone implements HNSW is that it's very simple to implement. So I've got on the right a diagram illustrating doing a search in HNSW. The NSW stands for Navigable Small World, and that refers to a way of constructing the graph so that it's connected, meaning that I have a good chance of being able to find what I'm looking for. And the H, the hierarchical, means what this diagram shows, that I have multiple layers. So layer 0 in HNSW mean I will have all of my vectors in layer 0, But in layer 1, I will have 10% of the vectors from layer 0. In layer 2, I will have 10% of the vectors in layer 1. And in this diagram, it's not actually reducing it by 10% to keep things simple, but that's what it looks like in practice. So what you do to search for a vector is you start in the top layer, which is represented by the red dot. The red dot is my query vector. So I'm going to find the vector in layer 2 that is closest to the red dot. There's only one vector in layer 2, so that's an easy decision. Then I go down to layer 1 and I start my search where I stopped in layer 2. So I start in layer 1 and I'm looking for the closest vector in layer 1, and it's one edge to the right of my entry point. So I take that closest vector now and I go to layer 0 and I start searching from where layer 1 stopped, restart the search in layer 0. So the point of having those multiple layers is it accelerates my search because I'm only having to search for through a much smaller graph to start with, and that gets me to the right neighborhood of the next layer down. So this actually ends up being a logarithmic algorithm to do vector search. So Lucene implements this, Weavy implements this, Quadrant implements this. We saw in the previous slide, Glass implements this. And this is what Astra implemented when we launched our public beta in June of 2023. So in more detail, I took the HNSW from Lucene and I rebuilt it to be a non-blocking concurrent construction algorithm because that's a better fit for Astra instead of being single-threaded only. And then that's basically what we launched with. The problem with that is that HNSW is well known for, and not just HNSW, but most graph algorithms, HNSW is well known for requiring a lot of memory. The graph is large, first of all, but more important, you're performing a lot of comparisons on large vectors that are accessed more or less at random. So in a traditional database environment, you have an 80-20 principle that almost always applies, which is that 80% of your queries are only concerned with 20% of your data. So as long as that 20% of hot data fits in memory, or you have enough IOPS to retrieve the part that doesn't fit in memory, you're in good shape. And the problem is that graph-based vector search does not follow the 80-20 principle. You have almost exactly the same probability of referencing any vector in your index as any other vector. And so what you can do, the best you can do, is I can keep the top layers in memory because that's guaranteed to be only about 10% of my data. So I can afford to keep that much in memory. But even with those top layers in memory, searching that bottom layer where effectively every vector is randomly accessed, it's brutal. And so I knew that was a downside, but I didn't know how bad it would be. And here's how bad it was. So this is a flame graph of doing a vector search against that HNSW implementation for a data set that doesn't fit in memory. So this was what this works out to was about 65 gigabytes of vector data and another 40 or so gigabytes of the graph index itself is also pretty large. And we're serving it from machines with, I believe it's 32 gigabytes of RAM. It may be 64, but either of those numbers is smaller than 100 gigabytes that you need to fit all of it in memory. So what you see in the flame graph is that there's no flames. Instead, you have one big mountain where if you skip past the purple parts that are JVM internals, the first brown line is read floats at. So that's our code, pulling a vector off of disk to do a comparison and say, am I getting closer to my query by visiting this node? And then there's a smaller part on the right that says read int. That's reading the graph structure off of disk. So over 95% of my search time is pulling stuff off of disk. So if I remember correctly, we were hitting something like 60 queries per minute. So around 1 query per second, not fast. So I went back to how can we solve this? Like, what is the state of the art in dealing with data sets that are larger than memory? I think most people would agree that these two papers represent the current state of the art in larger than memory vector search. So the left one is DiskScan, and that's it's also a graph-based algorithm. And on the right is SPAN with a P. Both of these, interestingly enough, are from Microsoft Research. And if you look in the lower right of the SPAN excerpt here, you see it saying experiment results demonstrate that SPAN is 2x faster than the state-of-the-art solution DiskScan. So 2x faster. So I took a good look at SPAN. However, I ended up deciding to implement DiskScan instead for two reasons. First, SPAN is not a graph-based algorithm. So converting my existing HNSW code and getting it to work well in a backwards compatible way with a non-graph-based algorithm, it's doable, but there's a lot of complexity there. And I wanted to ship an improved version of vector search in a small number of weeks and not in 6 months. The other reason is that DiskScan is used in production by Microsoft Bing, and the code is public. If you search for DiskScan GitHub, you will find Microsoft's repo where it is still actively developed. And so that gave me a feeling of confidence that if I ran into part of the paper that wasn't clear, I could always go look at the C++ code and figure it out. And that did turn out to be useful several times. So the way DiskScan works is there's two differences from HNSW. The first difference is that the graph building algorithm, which is called Vimana, and I may not be pronouncing that correctly, but the graph building algorithm, instead of making multiple layers, it simplifies it down to a single layer, but it allows adding longer edges in a carefully controlled manner so that you get that same property of being able to get to the right neighborhood in logarithmic time. So on the left, this is a graph that is following the HNSW minimalism principle. And then on the right, this is how Vimana adds longer edges to it. And this actually turns out to be very relevant to the ability to construct it in parallel quickly. So when I implemented the concurrent HNSW, I actually ended up having to do a kind of software transactional memory to keep the construction correct as multiple threads are modifying it at the same time. Because if you modify different layers and those changes are visible at different times to the other threads, you can end up not being able to navigate properly to the next level. So I had, like I said, it was fairly complex to fix that, and also support concurrent construction of the index. But with a single layer, it's much simpler. You don't need that transactional approach, and so that consequently makes it faster, which is end users don't care about how complicated your implementation is, but they do care about it being faster. So that was nice. The other big piece of DiskAn is that it uses product quantization to compress the vectors, and then it keeps the compressed version of all of the vectors in memory. So I'm performing the search 100% in memory. I don't have to touch disk except for an optimization to make recall better that we won't discuss here. But effectively 100% of my search is in memory. And so the way product quantization works is I have this large vector, 384 or more dimensions, and I'm going to break that into chunks of subvectors. So let's say I'm going to compress it by a factor of 16 down to 24 subvectors that are 1 byte apiece. So what I'm going to do for each of those subvectors, those 16 dimensional subvectors, I'm compressing them down to a single byte. And the way I do that is I partition all of that first 16 dimensions across all of my vectors. I'll look at those first 16 floats, and I'll treat that as a separate vector, and I'll compute a k-means partitioning of those. And I'll say, I want you to find the 256 most distinct centroids of those subvectors. And I'm choosing 256 because that's how many I can index into with a single byte. So I've got 256 centroids, and I'm representing the first 16 dimensions as a single byte. Then I do the same for the next 16 dimensions. I compute a k-means partitioning of 256 options. I represent that as a single byte. So it's a lossy compression because I'm approximating the original subvectors with one of these distinct centroids. But it turns out that if I'm compressing it by a factor of 16, then that is accurate enough to give me very good results. I'm not giving up on the recall. And in fact, I'm giving up a small % on the recall, but I can make up for that by just searching deeper in the graph. And I can search deeper in the graph because doing these comparisons in memory is so much less expensive. So there's a couple places I promised in the title slide that I was going to talk about how we used Panama to do this. So there's a class called SIMDOps in the JVector source code, and this is all Apache licensed. So SIMDOps contains a bunch of methods, and most of them look a lot like this, where I take 2 vectors, I take some offsets, and I'll show you why the offsets matter in a second, and why it's not just we do the whole vector every time, because a lot of the time we do want to do an operation across the whole vector, but there's a specific place where we need to do it on subvectors, and I'll show you that on the next slide. But you can see the purple highlighting here, I've highlighted the sum variable. So sum is a float vector, and that's a class that comes from the Panama vector module. And so we're going to initialize it to 0. And the species preferred, this is part of where Panama kind of abstracts the hardware for you as a Java developer to make your life easier. Because there's different CPUs and they all have different SIMD hardware available. So on Intel hardware, you have AVX2 is the oldest. You have AVX 256, which is what my desktop machine has, and you have AVX 512, which is the newest. And so Panama detects which is the largest chunk of bytes that we can work with at a time, or bits actually, it's the number of bits. And it says that's my preferred type of vector operation. So I can go through that now, and I have the loop that's labeled process the vectorized part, and I'll just go through this float array that I have that's my that represents my vector data, and I will wrap pieces of that float array in chunks that are the preferred length. And then I'll ask Panama to do two operations because I'm computing the dot product. I'm going to multiply those two subvectors together at element by element, and then I'll sum up the results of doing that multiplication. And then the final piece is the last purple highlight where it says reduce lanes. And so that's basically the equivalent of reduce in the MapReduce functional programming. So it's saying apply the add operation across all of the elements that we have left over in the sum vector, and that's our result. And then the last piece is just saying, hey, if we didn't evenly divide by this preferred bit size, then I'm going to do that in a manual normal Java loop. I showed you, this is the conceptually easiest part, that, hey, this looks basically like normal Java operations, except I'm applying it to multiple elements at the same time. Like that's all SIMD is fundamentally. Here's something that you might not have seen before. I hadn't seen it before. My colleague, Jake Luciani, committed this optimization, I think it was 2 days ago. So very, very recently. So there's an operation called FMA. And it's not just a vector operation. It's actually in math.fma. Just like you have math.min and math.ceil and a bunch of operations on floats and doubles, you have a math.fma on two floats or two doubles. And what that stands for is fused multiply add. So when I have one vector object, say a.fuse multiply add, and I give it as parameters a second vector object, actually two more vector objects. The first one I'm going to multiply a by, and then the second parameter I'm going to add the result of the multiplication into that second vector. And so this is it's more efficient in the vector world. And in the non-vector world, the reason that you would use it is that it reduces your floating point error. So if I do a multiply and then an add, I'm rounding my floating point values twice. But if I do the fused multiply add, it only gets rounded once. So you end up with a more accurate result. So that was a today I learned for me 2 days ago. So I said I would talk about why the offsets are important. That's because when I'm doing the comparisons between the query vectors and the compressed dataset vectors, when I'm searching through the graph, I would like to, the obvious way to do that is to encode, or is to decode the dataset vector that I've compressed. The obvious way is to uncompress it and then perform a normal dot product. But I can get the same results by computing the dot product with those centroid vectors, which are called my list of centroids, my list of 256 centroids, that's called a codebook in product quantization. So I'm going to look up my codebook centroid, and then I can do the dot product of those first 16 elements, then the next codebook centroid, the dot product of the next 16 elements. And I can do that without ever having to fully uncompress to a new copy of the vector. And when you're doing, I'm sure this is something familiar to all of you. When you're doing high performance code, whether it's Java or C or Rust, copies are the enemy. You want to do as much as possible without copying your data, because if that's in a hot loop, it's going to take a lot of your time. So that's where the offsets come in. As you can see in the lower right, centroid subvector is highlighted in purple. We're calling vector util.dot product, and we're giving it centroid subvector length, as that's how much of the dot product that I'm going to compute at a time. So that brings, I've said the word JVector a bunch of times. So JVector is where DataStax has open sourced the low-level search engine that does everything we've talked about. And so, like I said, yes.
Yeah, I have one query. So currently your similarity algorithm operates at FP32 granularity, right? So you use the float vectors, which are FP32 vectors. So what if we introduce FP16 vectors? So will that speed up the query processing?
So if I were doing raw vector comparisons, then yes, F16 is almost twice as fast as F32. But since I'm quantizing them down to single bytes, I don't want to quantize it twice. So I'm gonna rely on the product quantization to do the compression instead of quantizing it down to F16 and then compressing it. So we've open sourced this as JVector, Apache licensed. The screenshot is from around a week ago. We passed 1,000 stars on GitHub yesterday. So would totally appreciate your stars. We got to actually #1 trending project on GitHub briefly. And so it's good it does help to get people to look at it. And so here's a little performance comparison. So I mentioned that we started with Lucene. We deployed Lucene to our public beta, and actually a month later to production. And so I did a comparison between the Lucene HNSW implementation and JVector for a 100 million vector data set that was larger than memory. And I just did a quick test on my MacBook. But what this was roughly 60 gigabytes worth of data. So over twice my memory available. And you can see that JVector is murdering Lucene in the throughput available. And by the way, this is at equivalent recall. I didn't put a graph on, but it's not, oh, it's faster, but the recall is much worse. No, this is equivalent recall. So basically it works. Like switching to a better algorithm gives us better performance.
Jonathan, so maybe, I'm coming from the application background. I'm using Lucene for my search and all those stuff. So is JVector also provides faceted search, or it provides only the free text search?
JVector is just the vector search. So you could wire that up. Like if you're using Lucene with your doc IDs and so forth, it would be pretty straightforward to wire it up to using JVector. And in fact, one of the Lucene committers suggested that I contribute, is it called a module or a plugin to Lucene to do that? I'm not sure if I'm going to have time to tackle that, but yeah, it's totally possible to get Lucene and JVector to play nice together.
Basically, I mean, you got a very interesting point. My question is, at present in production, for example, we have an e-commerce app which use both for the free text search as well as faceted search. It uses Lucene. In that case,
Yeah.
can I still add JVector into it? Your answer is you can still add.
Yeah, so what Lucene does under the hood when you do a faceted search is it does the non-vector search predicates first, and it puts those into a bit set of doc IDs. And then it passes the bit set to HNSW and says, restrict your search to these doc IDs. And JVector takes the same approach, that you can give it a bit set of allowed IDs, and then it will restrict its search to those IDs. So I said it's easy. I mean, there's for some value of easy. It's straightforward, but I'm actually not sure if the Lucene API gives you access to the right pieces to wire it up without hacking, without changing the internals of Lucene. Lucene likes to make everything private, and sometimes that makes life difficult when you're trying to use it to do something that they didn't think of. But my broader answer is that this, JVector is designed to be used in an embedded fashion. If all you need is vector search, and just consume JVector directly, I think that would be a great fit for something like IntelliJ that wants to find the most relevant code to get suggestions like Copilot out of. I think JVector would be a great fit for that. But if you want something more general, we've built that, but it's a cloud service. So DataStax Astra is our general purpose database. It's not just vector search. JVector deals with document IDs and vector IDs, similar to Lucene, but Astra deals with, hey, it's basically Cassandra enriched with vector. So you get, tables with columns that have data types, and you can have indexes on the other columns, and you can do a query that says, where timestamp is greater than last week, and sort the results by vector similarity. So that's going to give you a much more full-featured solution.
Okay.
So a few closing thoughts. I talked about how the OpenAI embeddings are much larger, and you should use E5v2. Some implementation details. I'll talk about this last bullet here. One of the things you want to do when you're combining indexes, like we just talked about, is you want to be able to predict how many comparisons that the index will need to do if you do a search that's restricted to a set of candidates from your other index. And that was actually a lot of work to try to get a prediction there that worked. And part of the problem is that with different data sets, you can see the lines. I've color-coded my data sets. All of the lines are linear, mostly linear, so it's a pretty good prediction. But the constant is different for each of them. So what I ended up doing is I use my average prediction at the bottom here for all of them, but when I do a search, I record how many comparisons it actually did compared to my prediction, and then I use that to improve the prediction next time. So I'm basically, even if it's a data set that doesn't look like one of these standard data sets, even if the distribution looks different, then I'm in pretty good shape because I'm adjusting it dynamically. So yeah, JVector's on GitHub. I just showed the URL for Astra Database as a Service, and I'm happy to take questions. And I will tempt my luck. I will start my video again, and we'll see how that goes. I can stop it if it turns out to overwhelm my uplink again.
Yeah, Jonathan, how far is JVector mature in terms of replacing Lucene?
I mean, discussed earlier, Lucene does a lot more than JVector. But if all you care about is vector search, then you should use JVector instead of Lucene today. I don't. But if you need all the other Lucene pieces, then it's definitely some assembly required, or maybe check out Astra if a cloud service is a good fit for you.
Okay, thank you.
My question is, I mean, I don't know whether that's a valid question, but that is what I see in my production application. We are using Postgres for our application. Postgres also now supports vector embedding. So do you think that Postgres embedding will be sufficient in some cases, or they have some serious limitations to use some dedicated solutions such as JVector?
Yeah, so Postgres is also using HNSW, or the most recent version of PGVector includes HNSW. So I would expect that the performance difference from JVector to PGVector, or from Astra to PGVector, would be similar to what I showed for Lucene. That said, if your data fits in memory, then maybe that's good enough. So I would definitely, I'm a big fan of starting with the simplest solution that works, and then optimizing when you need it. So if PostgreSQL is working, then great. Like come look at Astra if you outgrow that. But yeah, if it works, it works.
Got it.
I actually looked at the PGVector HNSW code, and like it's HNSW, so it's going to suffer if your data set gets large. But other than that, it looked like a pretty good implementation. So I had no red flags that I would mention.
So for JVector, I mean, how do you horizontally scale the data size for
So
large data set?
JVector itself is just the low-level search engine. It's designed to be embedded, so it doesn't do any horizontal scaling at all. So Cassandra does the horizontal scaling in Astra.
Okay.
Well, thanks for letting me join your group this evening.
Thanks.
And appreciate the questions, and I hope this was useful.
It was super useful. Thanks a lot, Jonathan, for joining and giving the great talk. Thanks, Adithya.
Yes, great presentation. Thanks.
Thanks.